Alright, so what are our goals today? So just to recall, so last class the class before we talked about empirical risk minimization, which allowed us to quantitatively define learning as just a computational problem, right? So you have to come up with this model, this parameterized family of predictor functions, define a loss function, and then it all became the question of trying to optimize, right? So find some parameters which minimize the cost function. Someone says I'm echoing very badly. Is that true for everyone, or it's the same setup as last time? Is this any better? Okay. All right. So, so we are looking at gradient descent, which we said is some kind of universal algorithm that we can try on any function or any time we are faced with trying to minimize some objective function. Especially if the function is differentiable, it takes this simple form, just these two lines really. And there are a lot of other things that you can do here. How do you determine the step size, when do you stop, and all those criteria. But at the core is just this one line, right? You take your current iterate and take a step along the gradient. And what we'll try and do today is answer many of the questions that you asked at the end of last lecture, right? Once we have an algorithm, we'd like to know when does it work, how fast does it work, and does it even work sometimes? Can you get stuck in some infinite loop and things like that, right? And once we kind of have a better understanding of these things, we can then go about trying to understand what's the best step size to use. What should be a stopping criterion? Should I just run for so many iterations and output the last one? Or should I do something else to determine the final output and so on? And one of the things, it's kind of hard to get or understand the importance of is in this class especially, we'll focus on theoretical stuff where we'll make some strong assumptions about the functions. And when you go into the real world and try to build machine learning models, you'll see that these assumptions are so far from reality. These are just not even applicable for the simplest models you might try in deep learning, for instance. But nevertheless, the thing is these models and the analysis that we do here is very important because many of the techniques that you use on these deep networks, accelerated gradient descent, the way you set the step sizes, the way you decide the stopping criteria, all of these were developed first for the simpler functions that we look at. So you should think of this, these toy examples and the analysis that we do as a way to determine what are the better algorithms that you would deploy in practice. Right? So the insights that we gain from here have had tremendous influence on practice, even if we started out with some dummy assumptions which don't correspond to reality. Okay? So that's something that keeps coming up again and again throughout machine learning. We don't have a full understanding of why that happens, why algorithms developed for these kind of strong assumptions still work in practice, but the insights here are very helpful in practice. Okay, so we have this gradient descent, and what we'd like to do is to understand when does it work and how fast does it work. So we have to make some assumptions, right? Without that, we won't be able to. What if your function is something crazy like this? If this is the function that you're trying to optimize, there's no way gradient descent would work, right? You can even come up with even crazier functions which have some, just squiggles infinitely. In any small width, you have many squiggles, then you're not going to be able to optimize it. So we have to make some assumptions. And there are fundamentally three assumptions that we make in machine learning, and two of them are pretty natural and pretty generous. The third one is very strong, but also the most important and most influential. Okay? So let's look at those assumptions, and then we'll look at some examples of common ERMs which do satisfy the assumptions, and then we'll try to understand what we can say about gradient descent under those assumptions. Okay? Any questions about this blueprint? All right. So, what are some nice class of functions that we can optimize for? So intuitively, I mean, don't overthink it. You might have seen the answer before, but if you're starting from scratch, right? So what are some minimal assumptions that you would need on your cost function, on your function that you're trying to optimize, right? At this point, you can also put aside ERM in your mind, even though that's the class of functions that we're going to eventually try and optimize. Just think that someone came up and gave you an unconstrained optimization problem. Here's my f, can you try and find me a minimum value? So what are some natural assumptions that you would like to have on the function? Some natural properties that you want the function to have. And I think again minimal, right? If the function is just crazily varying, then we won't be able to optimize it, right? So smoothness. So the way smoothness, that's the first assumption. Kind of it's a minimal assumption, right? You wouldn't think your learning function has some weird discontinuities, right? Once I change the parameters a little bit, maybe there's an amazing gap in the value, right? So continuity, that's what we are really looking for. But if I just say continuous, then in the computational world, it's not as useful, right? We have to quantify continuity. In this function that I drew here is continuous, but for all practical purposes, it might as well just be discrete, right? Somehow, if it's jumping too much in a small change, that's bad for us. So that leads to our first assumption, which you already identified, which is Lipschitzness. It's called Lipschitzness. It's really just a fancy term for quantitatively defined continuity, okay? And the name comes from calculus, but basically it says that f is L Lipschitz if so if I take two values x and y, right? I want to say that when x and y are very close to each other, their function values are close to each other. Okay, that's kind of continuity, right? When I take 2 points which are infinitesimally close, we want to say the function values are close. That's the calculus 101 way of defining continuity. But if you want to quantitatively define it, what would be one natural way? So I can say, okay, it's at most some number times how close x and y are. Right? So I'll say times x minus 1. Does this make sense? I want to say, in high dimensions, there are 2 points. My 2 parameter values or whatever, if they're too close to each other, then the function values should also be close. That's it. And often, in fact, when you try and do more sophisticated applications, you end up sometimes have to look at functions where how you define Lipschitzness is also important. Okay? In this sense, what distance do you use between the 2 parameters, x and y, between the 2 values? The most common and natural one for many applications is the L2 distance. Okay, just the Euclidean distance between 2 points in high dimensions. Okay? But in some applications, you might have to look at functions which are Lipschitz under some different metric.
Do you ever consider variations of the left-hand side of the problem?
We will. Just hold on to that thought for a second.
Okay.
And we'll get there that will be assumption number 2 in some sense. Okay? So this is pretty natural, right? This is like saying that, even if I forget gradient descent and I want to come up with any algorithm, Lipschitzness seems at least at the bare minimum necessary. Okay? And all right. So now let's think of gradient descent. Okay? All right. So this is good. Now for gradient descent, there is one more problem, right? You can argue that it's the same phenomenon occurring, but the thing is that for gradient descent, the update was something like you're changing with respect to the gradient, right? And we saw already when we implemented, when even in some toy examples, we saw that there was a case where the algorithm was just flip-flopping between these 2 points. Right, you jumped there, took a gradient, and then jumped right back. Why was that happening? At least in the things that we were looking at in last class, it was happening when the step size was somewhat big, right? And we definitely want to kind of prevent such behavior if you want to analyze gradient descent, right? Or at least understand when this might arise. Okay. So any suggestions on why that might happen and how we can identify such a thing?
So the step size should depend on L somehow?
It should depend on L, but also if you realize here, what's happening is the step size should definitely depend on L, okay? And in fact, there is an analysis of gradient descent just under this assumption, just under Lipschitzness and convexity, okay? But that's kind of a bit more sophisticated, and the second assumption that we're going to make makes things easier and still, pretty widely applicable. So the second assumption here is that if you look at this picture, what's happening is that not only is the function non-Lipschitz in this tiny window, in the sense that it's kind of changing a lot when I change the value, but what's happening to the gradient?
It's like reversed.
It's like reverse, right? So gradient is also changing a lot here. Okay? So a stronger form of assumption number 1 is called smoothness. I mean, I don't know why it's called smoothness, because I feel like in the first one itself should have been called smoothness. But, that's what people in optimization have been calling it for like 50, 60 years, so we can't really change the terminology now. Okay? But they say F is beta smooth, right? If the gradient is a Lipschitz function. Okay, somehow you're talking about the change of the rate of change. Like, if you think of physics, it's like acceleration, right? So somehow it's saying acceleration is bounded. So here, like the gradient went from being positive to negative under a small window, right? It went from like 1 to -1, which is very bad. It means there's like a very pointy corner, which might be bad for us. Okay. So a stronger form of assumption 1 is that the gradient itself is bounded. Okay. So I have gradient is a vector. It's saying the distance between 2 points, the gradient that evaluated 2 points, is itself bounded in terms of how far these 2 points are. Any questions about this assumption? I mean, it's a very important one we'll use again and again throughout this course because it makes things easier for us and it's natural enough. Okay? All right. So there's another assumption that we'll make, but that will come later on. I'll say a few words about that in a little bit. So do you have a reasonable example of a function that is smooth but not Lipschitz? Basically, smoothness already implies that the function is Lipschitz. Smoothness is a stronger assumption than assumption 1. Okay, but I just wanted to make this difference because often when you try and read literature, you'll find analysis for Lipschitz functions, you'll find an analysis for smooth functions. But smoothness is stronger than Lipschitzness.
Is it sort of like smoothness is to Lipschitzness as differentiability is to continuity, sort of like?
Yeah, exactly, right? So like Lipschitzness is somehow saying something about the function being continuous. Smoothness is like, it's kind of the second order changes in your function. It's talking about second order. And in fact, there are analytic ways of defining smoothness in terms of the second order partial derivatives of f. Okay.
I have one question. Why did you switch the notation from omega of t and omega t minus 1 to x and y here? Could that be switched back?
Sure. So the only reason I'm switching that here is in defining functions, somehow x and y are just so ingrained in our blood, right?
Yeah.
If I start using u, v, w, I'll have to use u, v, w, and so on, which I'll try and stick to one. But in defining functions, somehow x and y is a bit more. That's what I'm more used to, really.
No, that's great. Thank you. I just want to make sure I wasn't missing something.
Yeah, definitely. That's a confusion that often happens. But remember that right now, there is no ERM beneath what we are doing. We just have function f and we're trying to optimize it. Okay, and x and y are just some two arbitrary points. And I'll try to stick to maybe u, v, w whenever I can. Okay? All right. And there's one more assumption, which is, I think, these two are things that, if you sat down and had to come up with assumptions, even if you didn't know anything about calculus, any history of anything, you might come up with these two assumptions. The third one, I think, is you need to have some context for that, and that is convexity. And it's a very, very important one, important concept, and hopefully some of you have already seen it in some form or the other. And you'll say that f is convex. Right? So when is a function convex? Basically, if I look at the curve of the function, then the chord joining any 2 points is always above the curve in between. Okay? So if I have u here and v here, and this is the chord joining u comma f of u and v comma f of v, right? And the claim is that this curve, this line is above the curve in between. Okay? So mathematically, if I look at any point between u and v and look at its function value, it should be below the corresponding value on the chord. Alright? If that's the pictorial definition, and mathematically, if say for all u comma v in Rd, f of u plus v by 2 is less than or equal to okay. It's saying if I take 2 points and evaluate the function at the midpoint, the value at the midpoint is less than the average of the two values. Okay? It's kind of the most succinct way of defining it, and there are many equivalent definitions of it. Okay, so for example, so let's say this is equivalent to saying so it's not just at the midpoint, when evaluated at the midpoint, it's less than the average of the two endpoints. But if I take something which is maybe 0.1 toward from u and 0.9 away from v, the same inequality holds with the kind of scaling. Okay? Does this make sense? So pictorially is just saying that the chord is always above the curve in between. Any questions? All right. So, I mean, we made these three assumptions. The first two, I'd say, are pretty natural, and almost all applications, however, deep in the practical stuff that you are, pretty much forgiving. The third one is the exact opposite, I'd say. Especially in modern machine learning applications, convexity is almost never satisfied. But as I said, that shouldn't make you kind of underestimate the importance of this class of functions, because almost all the algorithms that have amazing practical utility were first developed in this context and then applied to other functions. Okay? All right. So, I mean, convexity is such a deep concept in if you go to analysis, operator algebra, linear algebra, things like that, there's tons of applications. In computer science also, because convex functions have such amazing properties that they're widely applicable. All right, so let's do one example just to make sure we get some sense of these three properties, right? So recall the ERM problem with L2 loss function, right? So there we said, we took the linear predictors as our prediction family, and the cost function was, the loss function was a minus b whole square, right? So the parameters family was okay. So here the loss function we said would have been something like this. You look at your prediction at a point minus the value on the input point xi squared, right? And we also wrote this as xw minus y squared. Okay? So what is the gradient of this function? Well, it's not important to remember it really, but there is a formula for what the gradient is, and it turns out to be this guy. Right? You can evaluate it just by taking partial derivatives one step at a time, and you get this. Okay. But you can see here that the gradient seems pretty nice, and we think it is smooth with some bounded beta. Yes or no? So the thing is, you have to remember that the beta smoothness means that the change is bounded irrespective of where in the space you are, right? So here that is true because basically if I look at gradient of LOW minus some other point, let's say, okay, let's do U and V, that's going to be right? So the difference is this much. And you want to bound this in terms of how far U and V are. And it seems natural that, it seems reasonable to expect that there is an absolute bound on this change in terms of how far U and V are. Right? And even though it's not important for what we're going to do in the next few lectures, if you know some linear algebra, you can bound this as is the norm of this guy and there's something called the spectral norm. And you get this. Okay? So if you don't know what spectral norm is, don't worry about it. But basically I'm saying least squares regression is a smooth cost function, leads to a smooth minimization problem. Okay? And in fact, you can use this and some composition theorems to show that pretty much many functions that you come up with are in fact lead to smooth optimization problems. Okay? Alright, but how about convexity? Do you think the least squares cost function is convex? Well,
Yes, it's a
yes,
quadratic.
quadratic, exactly, right? So convexity, one of the reasons it's so widely useful is that it has some closure properties. Okay, so meaning that when you compose some functions which are convex, you'll also get a convex function. And that's very important. So meaning, for example, you know, f comma g are convex implies f plus g is convex. Okay? And f is convex implies a times f is convex. If I scale the function by positive number, it's still going to be convex, right? You know, you're scaling the curve, but you know, the same geometric property will hold. Okay. And perhaps the most useful composition property is that suppose I have a univariate function which is convex. Okay. And I have some vector A in Rd. Now I define a function GA in the high dimensional space, which is GA of W is G of A comma W. Right? You know, I have a univariate function. I take the inner product in high dimensional space and then apply the univariate function. Right? And basically in this setup, G is convex implies this high dimensional function is convex. Right? And this is what allows you to show that the least squares cost function is convex basically, right? So for example, it will also allow you to show that something like crazy, like, you know, let's say I define right? So e to the inner product a comma x, this is a convex function. Right? Because e to the x is convex and I'm just taking some things and you can just go nuts after this. You can do all kinds of stuff. Okay? So these closure properties are very helpful, especially if you think of recursively composing functions, then you get convexity if each one is somehow convex. Alright, so we have these three properties, and why did we start out on this journey on talking about these properties? Because we wanted to say something about gradient descent. Okay? And what is known about gradient descent? Right? You can really build, since the algorithm is so widely used, there is very fine-grained analysis of gradient descent. Right? You know, what happens if assumption 1 only holds? What happens if 1 and 3 hold? What happens if 1 and 2 hold? What happens if you have 2 and 3? Like, you can go nuts with all kinds of combinations, and we have good bounds on each of these combinations. But if I start doing that, then pretty much we'll take the entire course from now on. But we'll focus, that's why we'll focus on just one or two cases. Okay? So what we'll try and show is that following. So our goals. Okay, so we'll first start by showing that gradient descent is not like, a really wasteful algorithm to use for smooth functions. Meaning it might not get you to the best one, but it will make some progress. You won't have this crazy scenario where it will keep flip-flopping between two values, or it keeps increasing the value of the function. It's not going to make negative progress at the very least, right? So it's some kind of monotonicity that we will show for smooth functions only. And we'll build on that and show our main result, which is that GD finds the global optimum for smooth convex functions. Okay, so if along with being smooth, your function is convex, then you will in fact converge to the global optimum. Okay? So that's our goals. But before going on, let me say a few things about the stuff that we're not going to cover in this lecture, in this course. Right? So just to make sure that you know these things. So remark, GD converges to global optimum for Lipschitz convex. So even though we're going to analyze it for smooth convex functions, GD in fact also converges with some different step size routine to the optimum for Lipschitz convex functions. But it converges at a slower rate, as we will see. I'll state the bound later on. But the proof is a bit more involved, and I don't want to do two proofs. I think the most important analysis is for the case of smooth convex. Alright? And the second thing, you might wonder, why study convexity? Like, it seems like a strong assumption. Why can't I just solve this problem more generally, right? And the thing to keep in mind is that it is NP hard to solve general unconstrained optimization problem. Right, so it is NP hard, meaning there is no efficient algorithm for finding general global optimization problems. Okay? In fact, the real scenario is even worse in the sense that it's known that to find what are called higher order local optimum. If you don't know what that means, just basically think of it as saying that if I don't have assumptions, then it's hard to get any kind of guarantee on what your algorithm will do. And it's not just for gradient descent, for any algorithm. Okay? So if you would like to know more about this, I can tell you more later on. But the punchline is that, without making assumptions, global optimization, as you'd expect, is a very, very hard problem. Okay? So when we come back, let's take a 5-minute break. And when we come back, I want to go over 1 and 2. Okay? All right. So let's take a break of 5 minutes and we'll resume at 10:40. There's a question, what is the meaning of spectral norms or the subscript SP? SP is notation for matrix spectral norm. We'll talk about this, in module 2, but it's just something that only depends on the matrix and it doesn't depend on anything else, and we'll quantify that later on. But you might have seen it in a course on linear algebra if you have taken it before. But if not, it's not something that we'll use in the stuff that's coming up. Okay? All right. So let's try and show the step 1. And there was an important question in chat, but let me also announce it here, is that the Gradescope invitations will go out today. I was waiting for the class roster to somewhat finalize, and you should receive a link for registering on your official CCLE email today, and the assignment will be posted on Gradescope. You have to upload your submissions on Gradescope. And number 2, it will also be posted on EdSTEM under this lecture later on. And it will also be posted on the course website. So it will be on all three places, just find it wherever it's more convenient for you. And it will be up today at 6 p.m. Okay? And it's due next Monday at 10 p.m. That's the usual schedule for all the assignments. And the assignment will cover the first 4 lectures. So, some problems we'll also talk about the next lecture that's coming up on Wednesday. But you can already get started, I think, with most of the assignment because that will only involve the first 3 lectures. Okay? And we only have 1 officer coming up this Wednesday, but if you have any questions, you can just post them on EdSTEM, and hopefully you will answer each other, or if not, I'll check it frequently enough. Okay. Oh, there's a question, will you post answers for homeworks 0 just for us to check? I was not planning to, but if you have any specific questions, just let me know and I'll be happy to answer them. Okay. All right. So let's talk about what does gradient descent do for smooth functions. So as we said, one of the least things that you expect is the algorithm to not destroy progress, right? You're doing this gradient descent, the hope that you're converging to global optimum, you're decreasing the function value, but let's make sure that it doesn't actually increase the function value. In the simulations, that was actually happening, right? In some of the simulations, the function value was actually increasing instead of decreasing, right? And our first result, I'll say it's a theorem, is that if step size is less than or equal to 1 over L, so you have to take a small enough step size to get some guarantee on convergence or improvement, right? If I take a huge step size, I'm going into a space that is not local in any way. And recall that the intuition for gradient descent is that locally you're making some progress. So you have to be a little bit conservative in step size. Then f of wk plus 1 is less than or equal to f of wk minus Okay, so let's parse this. Okay, so recall that the algorithm was so I'm saying eta is the step size. So I decrease along the gradient by some number eta. And it's saying at least the function value decreases. Right? So let me call this FD. We'll refer to that as just FD, a shorthand, function value decreasing. Okay? Right? Does the statement make sense? Okay. So how do we prove this thing? It seems pretty useful, right? It's saying you're making some progress. You're not going to increase your thing, and the decrease is somehow also quantified, right? You're making progress, which is in some sense proportional to the norm squared of your gradient. It also kind of, makes some intuitive sense, right? If the gradient of the function is 0, then your algorithm is not changing. So in that case, your function value is also not changing. At least it has a simple sanity check goes through. Okay? So how do we prove this theorem? Why is this even true? And the proof, again, as we'll see, is important not just because, it's some property that we care about, but we'll see that the proof suggests how you would choose the step size in practice. Okay? It suggests tricks that people actually use in practice. So the proof of the theorem involves one nice property of smooth functions. Right, so here, let me use different notation. So f is beta smooth. Right, so we're talking about smooth functions, and in this case, you make progress. All right, so if you use something called Taylor's theorem from calculus, smoothness implies something which is very useful in analyzing functions. And what is that? So basically, you have your function, it could be something like this. Right now, we're not saying anything about convexity or making any other strong assumptions, okay? But if the function is smooth, it gives you some upper bound on the function value at each point. So what do I mean? It tells you that at every point on the curve, there is a degree 2, like a parabola that you can draw, that will always be above the function. So something like this. And if I go here, there will be another parabola. If I go here, there will be another parabola. Okay? So in particular, for all u comma v, f of v is less than or equal to f of u plus okay? So saying if your function is smooth, and imagine I fix the point u, then for any other point v, there is an upper bound on the function value where I can bound it in terms of a different curve, this parabola, this degree 2 curve, which I show in blue here. There's a question, does it matter how small or big this parabola is as long as it's tangent to the line? So basically, the closer it is to the actual curve, it's a better approximation, right? So this equation is saying at least I can find something which is not too far from the actual curve, and it's always above the function. Okay? And this curve, it imagine putting it on any point along my actual function, right? But locally, saying here somehow, if if I take anything here, if this is v, f of v is less than or equal to the value on the blue curve. Does that make sense? Does the statement make sense? Alright, so the proof of this, I won't prove it completely, but I'll just sketch it and we'll take it for granted for what's going to come up. So how do you prove such a thing? There's something called Taylor's theorem, and if you've taken Calculus 101, you know Taylor's theorem, which tells you how you can approximate a function at another point using the derivatives at some other point, right? So if you know calculus, in the one-dimensional case, it was something like so you'd have seen some expression like this, right? But there's actually a more refined form of this theorem. So let's say let me just write it as the. I don't know if you've seen the remainder theorem version of Taylor's theorem. How many of you have seen it? Okay, so basically, usually you write it as this infinite series, but there is a closed form expression for what comes up when I stop, and that's called the remainder term, and that's something like this. Okay, there's a formula like this for the remainder term that shows up in Taylor's series, and there is a higher dimensional version of this, and you just have to apply that. Okay, so if you know calculus, then it's a couple of lines of using this expression, but if you don't know calculus, then I'm not going to be able to prove Taylor's theorem, so let me not belabor at this point. But so take this statement for granted for now, and in the homework I'll ask you to try and prove this, just because I think it's something that you just play with and figure it out. Okay, any questions about this? About the statement, it's basically giving you a bound on what the parabola is doing, right? And if you go back to this theorem 1, so the bound here basically says something like this. The progress that you make in a single step of gradient descent is as good as the progress that you would make if the curve was actually just a parabola. Okay? So that's the intuitive way to figure, if you don't remember the quantitative thing ever. It's as if saying, okay, let me imagine I'm trying to optimize this blue function, and I'd make some progress in that case, and the actual value I get is at least as good. So proof of function decrease. Right? So what do we want to say? We want to analyze this f of wk plus 1. What is this guy? This is f of wk minus 1 over beta. Minus eta times gradient f of wk. Okay? And let's work with eta equals 1 over beta, just because it simplifies the calculations, and the same thing would work whenever it is less than or equal to 1 over beta as well. What do we get? So let's use this blue curve upper bound. So we know that this is less than or equal to this plus gradient f of wk comma wk minus wk inner product plus beta by 2 times, wait, what did I write here? Yeah. Okay. So let's just plug in the values and then you'll get this is wk plus the difference of the two things is minus eta times the gradient, right, which is 1 over beta. Okay, and then I get the norm squared of and eta is again 1 over beta. Okay, and now we are basically done, right? What's the inner product of a vector with itself?
The norm squared.
The norm squared, right? So I just get, I'm getting minus 1 over beta times the norm squared and I'm getting 1 over 2 beta times gradient. So you are making progress. Okay. Again, the intuition really is that you're behaving as if your curve was actually the blue one, and you make some progress there. And you know that whatever progress you make on the blue one is an upper bound. It's not true always, like it's not the best upper bound, but it is an upper bound. Right? So let me just draw the picture again. Basically, you are maybe somewhere like this, and if this is your WK, this might be your blue line, right? And this is where your WK plus 1 is, okay? And you're computing what's the value of the blue line, blue curve on WK plus 1. That's all you're really doing. And using that as an upper bound, okay? And keep this blue curve, kind of this sandwich, this parabola picture in mind, not just here, but analyzing gradient descent all over the place. It kind of shows up in many, many spots. Okay. So just these two lines has already showed us that under smoothness, gradient descent always makes some progress, which is kind of very cool, right? You know, we are not making negative progress, you are improving at least locally. Okay. All right. So what does this theorem tell us, right? So let's kind of understand implications of FD. Right? So it says that, you know, we make progress. Okay, and the second thing that's kind of useful is that so in the proof we used the step size was 1 over beta, right? But you know, this is very, very conservative, is too conservative for practice. if you think of some million-sized data set, often the smoothness parameter would be very tiny. So you wouldn't be able to use, if you use this bound, it won't at all be a good algorithm in practice. But then why are we doing it, right? It makes no sense to use this bound and say that, okay, in practice beta would be too small, too large, and then you get nothing. But the idea is that you can use the insight from the analysis to actually make progress. In the sense that what people do in practice, like your practical tricks, is you look for the largest step size, which gives you a bound just like in the theorem. Okay, because you know that that's kind of the best we can hope for. So let's try and mimic that. So what do I mean by that? So one trick is to find largest eta such that f of okay, find the largest eta such that this is true. All right, so the way you do it is, maybe like basically say, how would you, what's one maybe nice way of doing this in practice? Imagine I don't know the parameter beta, but I can guess it to some number. What would I do? I can kind of do binary search, right? So basically, if you look at many software, like let's say in Julia or in MATLAB, when they have unconstrained optimization problems, they will have some option to say that use some kind of doubling line search. What they mean is start with eta equals 1. If star holds, stop. Else, say eta to half current. And so you keep halving it each time until you find a value where the inequality holds. It's basically like binary search. And you'll get a pretty good approximation to the best you can do. Right? And you can see that this inequality, the specific form we are looking for, is something that's coming out of our theoretical analysis, and that again has implications in practice. And there's one more way of choosing eta, which is to do backtracking line search. So there are all kinds of tricks that people use. There's something called Frankel-Wolf algorithm, which is another way of picking the step size eta based on some form of such inequality. Okay? Any questions about this? All right. So now we showed that the function always decreases as long as we set the step size, in this aggressive way as 1 over beta. And as I just remarked, in practice you wouldn't set it so conservatively, but you choose it in a way so that something like this inequality holds. Right? Since it's then just a one parameter optimization problem, you can just do whatever you want. Okay? And so now let's try and analyze what happens about the global optimum. Like, you're just increasing or decreasing the function value a little bit, but maybe you end up something like this. Right? So suppose I start this is my W0, then I keep making progress and I come here, and here the gradient is 0. Right? And whereas the global optimum is all the way here. So the gradient descent algorithm would converge in this case, but it would most likely converge to this point. The one which is not really the optimum, but it's a point where the gradient is 0, so the gradient descent will stop changing at that point. Right? And how do we get around this? And basically, convexity tells you that such a thing cannot happen. If your function is convex, then you cannot have such a double dip structure. So why is that? For example, why is this function not convex?
Because
You can draw.
oh, go ahead. Sorry.
I was going to say you can draw a chord between the hump in the middle, that where the function is above it.
Right, so if I draw this chord, you can see that the function is above the chord. So this is not convex. And basically the reason convexity is useful is because it precludes such double dips in your curve. And if you, what it technically means, as we'll see, is that a local minimum is also a global minimum, right? Okay, so let's try and now analyze gradient descent for smooth convex functions. And this is going to be our first main theorem. So this lecture and potentially even the next lecture, it will be more theoretical. We'll try and understand gradient descent and some of its variations. And next Monday, we will again look at some applications of gradient descent and see how it actually performs and how we can tweak some things. Okay? So what is the main theorem, I'd say, for gradient descent is the following, which is that if f is beta smooth and convex, then okay, so let's parse this first. It's saying, let's say W star is a global optimum. And recall, we want to minimize the function, right? So we want to find a value which is as close to the global optimum as possible, not much more than the global optimum. It's saying if your function is beta smooth and convex, then you will actually converge, or you'll find a value after k iterations which is close to the value of the global optimum, depending on two things: your starting smoothness, right, and how close your initial guess is to your optimum value. Okay, and the main thing here is that as the number of iterations increases, you are converging. And there's a very quantitative bond on how fast you're converging. It's 1 over k. So if I want epsilon close, then I roughly have to do 1 over epsilon iterations. Right? And if you don't have smoothness, just as a remark, if you just know the function is Lipschitz, you can also show such a bound, but the rate is something like square root k. When people talk of rate of convergence, what they mean is how close am I to the global optimum in terms of the number of steps I've taken. So what you really want is that the number of steps increases, we're getting closer and closer and closer. Okay, and it's saying, it's not bad. If you want epsilon close, you need 1 over epsilon iterations. Okay, does the statement make sense? So just say, remark, it is known can get okay, it's not something we are going to analyze. And one thing to keep in mind here is that the step size also has to be carefully chosen. It has to keep on decreasing. And once again, as I said, the insights that you gain from analyzing these algorithms is very important practically, because it tells you how to set step size and how you can speed up things and so on. Okay? But this is not something we are covering. It's a little bit more advanced, and I think this is more insightful. All right, and the proof is actually a little bit tricky. I mean, I think it's very mysterious, even though people often think of it as, okay, it's just optimization theorem 101. It's just a page of some linear algebra, but it's, I think, very clever in how it's done. I don't know who was the first one to prove it. It's probably been discovered like dozens of times in very different contexts in 50s and 60s, but sort of folklore now on how we analyze it. Okay. So the proof involves two important components, right? So one is something that we already saw, right? Which is that function is smooth. If I say eta is 1 over beta, the step size is 1 over the smoothness, I get this quantity. So we already saw that the function value decreases, right? Even without convexity. But with convexity, we'll see is that the distance to the optimum also decreases in a nice quantitative way. Okay? And that, along with the fact that convex functions don't have this double dip structure, will tell us that the function converges to the global optimum. Okay? So let's start with that. So proof, we'll first show that distance also decreases into okay. So what do I mean by distance also decreases? That's what I mean. I mean, nothing very fancy. It's just saying that the distance has decreased. Okay? And how much does it decrease? Once again, it decreases by, I think, let's see, something like,
This is the distance from the starting point, not the optimum.
oh, sorry. My mistake. Distance to the optimum. That's what I meant. Sorry. Right. If the starting point is useless, that you don't want to converge to the starting point, you want to converge to the optimum. Right? Distance to optimum also decreases. So it's saying something stronger about your function, right? Wherever your global optimum is, you are actually converging to that, which is already something better than what you had for smooth functions. So that means that you cannot be stuck in this sort of local minimum, right? You have to converge to wherever your global optimum is as the number of steps keeps going. Okay? Alright, so I think just the fact that the distance decreases is already somewhat involved, and the quantitative version just comes out of showing that the distance decreases. So I just stated this version. I mean, I'm not 100% sure of this constant, but hopefully, if it's off by a factor of 2 or something, we'll come back and correct it. Okay. So how do we prove such a thing, right? It seems kind of counterintuitive, and I mean, not counterintuitive. It seems intuitive, but how do I go about showing such a thing? So to gain insight for that, so let's draw some pictures. So we have our convex function. I mean, if I draw a parabola like this, I don't know, it's hard to draw a convex function which is not a parabola, especially when I'm drawing it like this. But like you can imagine it's something like this. So I hope it's clear that it's not just a simple parabola, like it's kind of skewed in one direction. Now what do we know? We know that, actually let me draw a slightly different thing. Okay, so if a function is convex, we know that every chord, the curve in between is below the chord, right? So imagine, like it's saying, this chord has to be above the curve in between the 2 points. Now what happens if I keep taking this chord closer and closer and closer? What would happen then? Any guesses?
Would it become like close to the derivative?
Right. It would, like, if you think of just keep on shrinking these blue things closer, you'd get something which is just this, like the tangent line. Right? And what do you notice about this tangent picture?
It's under the curve.
It's under the curve. And it's not just under the curve locally, it's under the curve everywhere, right? And if you think of the double dip example, that was actually the problem too, right? So you had here, you could find, so you pointed out that if I take these two things, then the chord here, there was a portion of the curve above the chord. And if you keep shrinking these things, you'll notice that what's happening is that the tangent line, there's a portion of the curve which is below the tangent line. It's the same phenomenon that's happening, right? And in fact, the notion of convexity is equivalent to saying that the tangent line at every point is actually below the curve. Okay? And this is very important in our analysis, also kind of geometric intuition for what a convex function is. So let me write that down. F is a differentiable convex function. Implies tangent line is below the curve. Okay? And this is almost an if and only if statement. If I have a differentiable function, then it is convex if and only if the tangent line at every point is below the curve. Right? And let me call this the fundamental inequality of convexity, because I think it's kind of the equivalent definition of convexity, which is that f is convex implies. So how can I mathematically say that the tangent line is below the curve? What would be the mathematical way of saying that? Like in terms of equations and notations. Right, so I want to say that for any, this is my point, let's say u. Now this is my point u, and if I take any other point v, right? Then the red line has some value associated with that. And we want to say that the actual value of the function f of v is higher than the value taken on the red line. Right? The question, the derivative at a point is below the function less than. So it's basically that, but you want to say that any other point v, if I look at the tangent line, that's my defining curve, the value on that line is below the actual value of the function. So meaning f of v is less than or equal to f of u. If it were one dimensional, what is the equation for the line? It's f of u plus the slope times the slope is just the derivative.
F prime of u
Times v
times
minus
u, or v minus u.
Right? So it's like the slope of the line is f prime, right? In high dimensions, it's basically the same. You just replace that with inner product. So you get this plus gradient f of u comma v minus u. And sorry, this should be greater than or equal. Okay, so basically the right hand side here is just the equation for the red tangential line, and it's saying this is below the curve. And you can define convexity equivalently in this way. Any questions about this? Okay, so now we have some kind of a nice geometric picture, right? The smoothness gave us an upper bound at every point. It said at every point I can draw this parabola and it's an upper bound. And the convexity gives you a lower bound. It's kind of, both together really help us. So going back, so the geometric picture of beta smooth convex functions. Right, so the way to think about it is, maybe I have something like this. Okay, and at every point, if I draw the tangent line, that's going to be below the curve everywhere. And I also have a parabola that I can draw. Which comes from smoothness. Okay, does this make sense? So we will use both of these facts, the fact that you have this parabola and this line, to show that the distance decreases and that gradient descent converges to the global optimum. So let's say that this point here, from the picture, is my global optimum W star. What's the tangent line here? What would be the tangent curve?
Zero slope.
Zero slope. So it would just be the horizontal line, right? So kind of, that's not giving us too much information, right? Maybe let me use dotted. To distinguish from the other thing. But the parabola could still be useful. Right? And since W star is the optimum, we know that the parabola is actually centered here. Like, when we were at WK, so if you think of this as your current iteration, you were making progress. So there's still room to go on this parabola, right? But when you're at W star, the parabola, there should not be any room because you are already at the optimum. Okay? So let's now try and use this to argue that you make progress in the distance. The one-dimensional intuition is pretty much like, generalizes to the high-dimensional thing. You just have to replace products with inner products, but this picture is really quite informative. Now in this picture, where would Wk plus 1 be qualitatively? Which side of Wk would Wk plus 1 be?
Left.
To the left, right? So maybe you can think of all of this. This is the sort of W axis, right? And if I take a step, then this was your Wk, and maybe this is your Wk plus 1. Okay, so this is my Wk plus 1. Okay. Now for Wk plus 1, we want to say the distance decreases. So one way, one important way of saying that is that somehow your gradient should point towards W0. Right? So your derivative in this one-dimensional picture, the derivative better be to positive, right? Because you have to go in the left direction. Right? So we really want to say something like, so what would it mean to say that the distance is decreasing, that you're moving towards W star? Like we said, you have to move left, meaning the derivative should point away from W star, because when you take the negative of the derivative, you go towards W star. In high dimensions, what would the analog be? Like here, even in one dimension, what would the analog be? So if I look at this guy, this times this should be greater than or equal to 0, right? If Wk is to the right, meaning this number is positive, then the gradient should be positive, so that when I take negative of the gradient, I move to the left. So this is the one-dimensional intuition. If you want my distance to W star to decrease, I need to take a step towards W star. So that means somehow the gradient should point away from W star. Right? The negative of the gradient should be towards it. So what would be the high-dimensional analog of this? Any guesses?
Gradient.
Right, so the high-dimensional analog would just be that if I take the gradient and replace with the inner product, I want this to be greater than or equal to 0. Right? Because that will tell me something about how much kind of gradient points towards Wk minus W star. Okay? Alright, so with that intuition, let's try and get a control on this inner product. And as I said, there's a little bit of magic here in how you prove this thing, but once you see the answer, it's just 2 or 3 lines, but it's hard to motivate this step. Except for the fact that you want to say that you're moving towards it, so I want this product of the derivative with my how far I am to be positive, and then we'll quantify this. Okay? So how do I quantify that? So remember, Wk plus 1 was Wk minus eta times the gradient f of Wk. right? And let me first use the red inequality. What does the red inequality tell me? It tells me that hold on, actually, let me not do that yet. So for the proof, actually, what we won't exactly look at this wk plus 1, but we'll look at a slightly different point, or potentially different point, which is, let me call this w bar, which is w star plus eta times gradient of wk. Okay, so let okay, this is some point I defined, and if my intuition is right, this picture is right, this should be on which side of w star? No, the gradient should be positive, so it should be to the right. Right? Once again, like, always, it seems like, we're doing something silly by looking at the one-dimensional picture, but basically the analysis in one dimensions and the higher dimensions is pretty much the same. So this is my w bar. And basically what we'll do is compare the value of the red line on the red solid line on w bar and the blue dotted line on w bar. We'll compare these two things, the blue and red. Okay? So let me maybe use colors here. So what do we know? We know that this is the equation of the red line, and I'm looking at the red line at this point w bar. We know this is at most f of w bar, right? And let me now look at the blue line, the blue parabola. Okay, so I compared the blue dotted parabola to the red line. I mean, it's kind of this f sandwiches between these two, right? But what is the gradient of f at w star? Zero, right? So you already pointed it out, so I can get rid of this term. Okay, and what is w bar minus wk? This is, I can just plug in the value and I'll get eta times gradient of wk plus w star minus wk. And what is this guy? The w bar minus w star, that's just eta times gradient. Okay, and what else do we know about f of wk and f of w star? We know w star is a global optimum, right? So that means that right? So I'm expanding the first inequality here. I get that is less than or equal to this plus, remember eta was 1 over beta, like we said the step size should be exactly this much. So I just get right? And we know that wk, the function value, is at least as big as w star, right? So this implies that 1 over 2 beta times the gradient squared is at most okay. So what we just showed is that by comparing this blue dotted and the red line, we could tell that the gradient is indeed pointing towards w star. If I are pointing away from w star, meaning when we take the negative gradient, I move towards w star, which is our intuition, and we just quantified it right now. Okay? And once we have this, that then the gradient is kind of pointing towards w star, if I were to show that the distance decreases, what should I do? Right, so think again, go back to your high school geometry, right? I know that the angle is something and I want to compare the distance between 2 points. What should I do? Now here's my wk. I'm taking a gradient, going to wk plus 1, and then I have w star somewhere here. Maybe let me write it this way. Here's my wk. I'm moving to wk plus 1, and here's my w star. Right? So the inner product tells me something about this angle, right? The wk minus w star and the gradient. And if I want the dotted distance, what should I do? What formula would you use from high school? If it was a right angle, what would you get? You would use
the
Pythagorean?
triangle inequality.
exactly triangle inequality, or the more refined form of it, which is the cosine formula, right? So you can calculate the distance between 2 points based on the distance of the two vectors and the angle between them. So that's exactly what we are going to do, right? So if I'm interested in this distance, the Pythagorean theorem would have been something like right? But the cosine formula, you just get a correction term, which is the angle between these two things. It should be wk plus 1. Okay? This is just the cosine formula, or a higher dimensional version of it. And now we are pretty much done, right? Because I can write this as star square. And what's the difference between these two things, wk and wk plus 1? It's just the gradient. Right? And what else? We get 2 times this is the negative of the gradient, right? So I get minus of but we just showed something about the angle between these two things, right? So just plug that in. Equals okay. So by using this cosine formula, we showed that the distance is actually decreasing. Okay. All right. So let me, as I said, I might have been wrong about the constant. So let me go back to that, and let me just remove this term. If I set the step size to be 1/2 of that, I think you'll get that. But we just need the decrease for now. Okay, so we just showed that the distance decreased. I mean, I know it seems like a lot of arithmetic, but the basic picture is that we're using this red line and the blue parabola to get some information about the angle between the two things, the step you're taking and how far you are from the origin, from the W star. And once you have that, you use this picture. Okay. So in conclusion, right? So we just showed that the distance to optimum always decreases in the iterations of the algorithm. Okay? And in next lecture, we'll start from here and show the final property that we want, which is that it's not just that the distance decreases, but we'll actually quantify how fast it decreases. All right? And this will involve combining property 2, which is decrease in distance, with the decrease in functional value that we showed earlier. So we'll combine these two things to get a quantitative bound on how fast the function value is decreasing. Okay? So let me stop with that today. And in the next lecture, we'll finish this analysis of convexity and take insights from here to consider and develop variants which are faster and very useful and very important in practice. Okay? All right, so that's it for today, and we'll finish the analysis in the next lecture. Bye, everybody.
Hey, Professor, I had one quick comment.
Sure.
I was looking back through the notes in lecture 1, and it looked like one of the assumptions for ERM got deleted. You can obviously go back in the video lecture and get it, but I know it's a newer platform, so I'm not sure what happened.
Oh, we got deleted? That's weird. Oh, wow, yeah.
Yeah, that's there.
Yeah, that's kind of weird, yeah. Okay, so what was that? Yeah, cannot be right all the time. Yeah, that's true. That's weird. Yeah, I have no clue why that happened, but yeah, thanks for pointing it out. I'll correct it. I'll fill it in.
Okay, thanks a lot. See ya.
Sure. Okay.
Thank you.
Bye, everybody.